Yeah, it's the same thing. Yes. So, well, I can take the other half, right? So this is my U2, correct? So what is your U2? Well, is every x and y on the sphere, on the circle, sorry, such that what? X is negative now. Well, here is my phi 2. Here is your phi 2. It takes x and y and gives you what? Gives you what? Y. I'm still projecting on the y. But my inverse, phi 2 of y, gives you two things. What will be these two things? The y is y, that's fine, but the x is negative. Now it's negative square root 1 minus y squared, and I'm done. Are we done or not yet?
No.
Yeah, because I left out 2 points. I have to cover them. So you please, you have to come here and locally around the point, you have to cover, you have to provide a map, right? Well, I can have my map actually to map all these, the upper half, and project on the x now, right? And project on the x. Okay? I'll do this. I'll do this that cover the upper point for you. So let's do the U3, please. Is every x and y in S1 such that what? I'm covering the upper half. Y is greater than 0. Very good. And your phi 3 that takes x and y will give you what?
X.
Now I'm projecting on the x. So if I'm taking the x back, this is inverse. If I'm taking the x back, I have to provide you x and y. Well, the x is x, but the y is
1 minus.
square root 1 minus x squared, and I'm done. You need to add just the 4 math for the bottom part, and you're done. Okay, this is how we rigorously prove that something is a manifold. Manifold is the most sloppy word used in literature. People just say, oh, I mean, this is a manifold, this is a manifold, without really paying attention that this is the mathematical definition of a manifold. Any questions so far? Any questions so far? Like you see, it's not really depending so far on anything of our course. So this is really advanced stuff. So if you have any questions, don't feel ever shy. That's fine. We're just discussing. You learn from me something, I will learn from you other things. We always learn from students' questions and discussions, particularly when it comes to this advanced stuff. Any question? Any question? Okay, let's take a more serious example related to mechanics. Although this is related to mechanics, but it's more mathy, because this is the configuration space of a pendulum. And we're just proving that it's a manifold. Let's talk about a rigid body. And we're gonna come back to rigid body rotation several times in these 4 lectures, actually. Rigid body rotation. And the translation is easy, it's just as a particle, that's fine, the rotation is interesting. Rigid body rotation, do you remember what is the configuration space? And we didn't talk about the configuration space explicitly, if you can guess. How can you represent the rotation of a rigid body? The very obvious way that we even learn undergrad was that.
S1, S1, S1.
Say it again, please.
S1 by S1 by S1. Three
S1,
angles.
S1, S1. That's fine, but S1 cross S1 cross S1. Yeah, but it doesn't show the relative relations between the rotations. I didn't think about it. We can think about it later. Does S1 cross S1 cross S1 really represent a configuration space for a rigid body rotation? I don't think so, but I mean, we can think about it later. What are the things that we learned in this class? How do you represent the attitude of a rigid body? The orientation of a rigid body? Polar angles. This is the obvious answer, psi theta phi. But right? But what? But Euler angles, there has to be singularity. So we cannot use Euler angles here. Unless, because remember, the main essence of this that we want to do a global analysis, a global view. So I want to see the whole picture. You cannot tell me, hey, you can see almost everything except few points where theta is pi over 2 or 3 pi over 2. No, no, no. Okay, if I want to do this local analysis, I will not just pay attention to all these details. We want a global thing that works for every single possible configuration. If it's physically possible. Obviously, theta equals pi over 2 is a physically possible orientation for a rigid body. What is the intrinsic space? No, forget about space. What's the intrinsic representation for a rigid body rotation? When I'm telling you, here is a rigid body rotation, I can give you psi theta phi, that's fine. But I can also give you what? What is the intrinsic thing that I really should give you if I'm describing a rigid body rotation? What is that? Any guess?
Moment of inertia.
Moment of inertia? No, the moment of inertia doesn't tell you. Moment of inertia is a characteristic for the body. So it has nothing to do with the motion. No, I'm saying, well, we're doing some motion, I'm at some attitude, and I want to tell you, here is the attitude at this particular time. What I really should give you? The angular velocity will characterize velocity. But what about the attitude, the position?
Principle.
It's the rotation matrix, right? It's the rotation matrix, actually. When I give you the rotation matrix, I give you everything. Because remember, the rigid body attitude, what's that? It's how the body axes are inclined with respect to the inertial axes, right? And how is this intrinsically represented? This is by a rotation matrix. Every other thing that we do is that we're trying to construct the rotation matrix by fewer number of variables instead of 9 by 9 or 6 angles or whatever. No, here I can represent by 3 or quaternions is 4. But the intrinsic representation of the rigid body rotation is the rotation matrix, right? So what is the set of rotation matrices? Actually, this is the manifold of the rigid body, or if you want to say the configuration manifold of the rigid body is the set of all 3 by 3. Any matrix A that is 3 by 3, right? This is how we, right? A in R 3 by 3, such that what? The matrix has to be what? Anybody remembers? Not skew symmetric.
Determinant is plus or minus 1.
This is one thing, that's right. Determinant is plus or minus 1, which means what?
Columns or orthogonal.
Yeah, well, we have a very simple relation for it. That A times A transpose is identity, right? The transpose is the inverse. For this set of matrices, you can have determinant either being positive 1 or negative 1. So let's have a convention. We're going to take the determinant to be positive 1. But this is the real condition. It's an orthogonal matrix, okay? Actually, this has a name. This space has a name. We call it SO3, special orthogonal matrices, 3 by 3. The space of special orthogonal matrices 3 by 3. Any matrix that satisfies this condition, A times A transpose is 1, it has identity, and it's determinant positive 1, we call it, it's in SO3. Capital S, capital O, 3. Special orthogonal matrices, okay? So, actually, this is a manifold. This is a manifold. SO3 is a manifold. Every point in the manifold is what? Every point is what? It's a matrix, right? Every point is a matrix. Every point is a matrix. Every point is a matrix. It's a rotation matrix. Correct? Every point is a rotation matrix. So this is why I wanted you from the beginning to be as abstract. Yes, a manifold can be a curved space embedded in half-dimensional flat space like the board. Can be sphere, can be all these nice shapes, but it also can be a set of matrices. This is indeed a manifold. We're going to prove it right now. Okay? And if there is a single reason, if you want to mention a single reason why mathematicians can really flip the game, why they are successful, if there is any success attributed to them, it's because of their abstractness. Because they really are, they don't think of what we think. Well, the manifold is a surface. No, a manifold is not a surface. Well, a function is a function that x squared y. No, a function is a map between two spaces. It's their abstractness that really led to greater things, as we're going to see in this course. So this is a manifold. Let's just, I will not prove the three-dimensional thing, I will prove the two-dimensional thing, SO2. Okay? Is every special orthogonal matrices 2 by 2?